Okay, so we know mu alpha chemical potential of alpha phase is equal to chemical potential of beta phase, okay, when phase alpha is in equilibrium with beta phase. Okay. So, here we have alpha phase, and here is beta phase. They are in equilibrium with each other. So, from here you can write del mu alpha by del P at constant temperature times dP plus del mu alpha plus del mu alpha by del T at constant pressure times dt equals to del mu beta by del P at constant temperature times dP times del mu beta by del T at constant pressure times dP. Okay. And we know that del mu alpha by del P at constant temperature is nothing but molar volume of alpha phase, right? We already discussed. So, this gives you V bar alpha times dP minus, and del mu alpha by del T at constant pressure, we already know this is nothing but molar entropy of alpha phase. So, we can write S alpha bar times dt, and in the right hand side also similarly we can write S beta bar times V beta bar times dP minus S beta bar times dt. Okay, so we can write V bar, we can rearrange the things, minus V beta bar times dP is nothing but S alpha bar minus S beta bar times dt. So, we can further simplify this one as dP by dt is delta S bar transition, we can write by delta V bar transition, right. So, where delta S bar transition is nothing but S alpha minus S beta, and delta V transition nothing but V alpha bar minus V beta bar. Okay. So, we get this, and we know delta H transition is nothing but T times delta S transition. Okay. So, if we substitute this here, we get dP by dt is delta H transition by T times delta V transition. Okay, and this equation is known as Clapeyron equation. Okay. So, this equation is known as Clapeyron. So, dP by dt equals to delta H transition by T times delta V transition is known as Clapeyron equation. Okay. So, next we will consider the equation. So, dP by the one we already derived just now, we have already derived. So, dP by dt is delta S transition by delta V transition, and we also know dP by dt nothing but we just derive this delta H transition by T times delta V transition. Okay. And this equation, it relates the slope of the two-phase boundary line in a phase diagram, or to be specific in PT, pressure temperature plot, that we will see it today with the values of delta H transition and delta V transition for a transition between two phases. Okay, now we will consider the equation dP by dt so delta S transition by delta V transition. Now, we consider for solid ice to liquid water transition. Okay. So, here for this transition you have solid ice, it goes to liquid water. So, delta S transition is positive, right, because you have solid ice, it goes to liquid water. Okay. So, disorderness increases here. So, delta S transition is positive. And what about delta V? Delta V represent, as you know, change in change in molar volume, right. So, delta V transition means V of liquid water minus V of ice, right. Now, molar volume of ice is higher than molar volume of liquid water. So, this gives you negative quantity. So, it says these two conditions, they imply that dP by dt is negative. Fine. Okay. So, if we plot P versus T, then for the transition solid ice to liquid water, we get negative slope, right? And it says what further? It says that it further implies that melting point of ice decreases with increasing pressure, right. So, melting point of ice decreases with increasing pressure, it says. Okay. Now, you consider for liquid water to water vapor transition. So, in this case also delta S transition is positive, right, because liquid water goes to water vapor, so to chaosness increases. Okay. So, entropy change is positive. Now, what about delta V transition? So, delta V transition is nothing but V bar of water vapor minus V bar of liquid water. And we know molar volume of gas is much higher than molar volume of liquid. So, it gives a positive quantity. Okay. It says that dP by dt is positive, right. So, it implies that boiling point of water increases with increasing pressure. So, because dP dt is positive means we can say dt dP also positive, right. This is also positive. So, we have seen that if we consider the solid ice to liquid water transition, delta S transition is positive and delta V transition is negative. So, it gives that dP dt is negative, right. So, dP dt is negative means dt dP is also negative, which suggests that melting point of ice decreases with increasing pressure. And for liquid water to water vapor transition, delta S transition is positive and delta V transition is also positive. These two quantities, they imply that dP dt is positive, which says that dt dP is also positive, and this implies boiling point of water increases with increasing pressure. Very good. Now, we will consider solid ice to water vapor transition. And for this case, delta S transition is again positive, because solid ice goes to water vapor. Okay. So, chaosness increases. What about delta V? So, delta V transition is nothing but V bar solid ice minus V bar water vapor. Or the other way here actually, okay, because solid ice goes to water vapor. So, V water vapor minus V solid ice, and it is also a positive quantity because molar volume of water vapor is much higher than the molar volume of solid ice. So, it says, so these two they imply dP dt is positive, which says dt dP is also positive, right? And they imply that the sublimation temperature increases with increasing pressure. Okay, now we will consider the absolute, or we would like to quantify the delta V transition and delta S transition. Okay, let us see and how they differ for these three transitions. Now, delta V transition for liquid to vapor is very similar to that of solid to vapor transition, but okay. So, these two imply that dP by dt for solid to vapor is higher than dP by dt at liquid to vapor. Okay. So, we get a steeper slope for solid to vapor transition than that for liquid to vapor transition. Okay. Now, we know the phase diagram of water, but we are again drawing with the information we have now. Okay. So, this is pressure and this is temperature in Kelvin. Okay. Pressure in bar, suppose. So, we get curve like this, and this. Properly drawn here. Okay. So, here you get solid ice, this is the region solid ice, and this is water vapor, and this is liquid water. Okay. And if we draw a line like this, okay, so we get the point it touches here is, it is nothing but your boiling point, and this is this is the melting point or freezing point, whatever you say, and this is this point where all three phases here at this point they coexist. This is known as triple point or T3. So, T3 is the triple point, TB is the boiling point at pressure P equals to P1 bar. Here this is P1, and TF is the freezing point or freezing temperature and boiling temperature at pressure P equals to P1 bar, and T3 is triple point, right. So, triple point. So, this is, suppose this is our point O here, O, and then we can label O A, B, C, or triple point O. Okay. And here along line OA, along line OA, solid ice and liquid water coexist. Okay. Similarly, along line OB, or OB represents liquid water and water vapor coexistence line, and so on. Okay. So, what we discussed so far, we derived Clapeyron equation, and with the help of Clapeyron equation we could able to draw the phase diagram of water, or rather PT diagram of water. So far whatever we discussed, we consider ideal gas. Okay. Now we will consider non-ideality. Okay. So for non-ideal gas, Fugacity is the measure of non-ideality of a gas. Okay, so what is Fugacity we will discuss. So we know molar Gibbs free energy at constant temperature and pressure, we can write like and P0, here P0 or P0 is one atmosphere or 1 bar, whatever you consider. Okay, 1 bar. So P0 is 1 bar. Okay. How did we get that equation? We got this equation, or we obtained this equation starting from del G by del P at constant temperature, right. Suppose this is our equation 1 here and this is equation 2. And then what we did, if you see, look at equation 2, what we did, we basically did like dG is V bar dP, and for V bar we use the ideal gas equation. Okay, so n is 1 here, so V bar is nothing but RT by P, and then we integrated. Okay, on integrating, we get this equation, right? So we will now generalize equation 1 to the case of a real gas. Okay. Now the equation 1 will generalize for a real gas. So we consider a real gas equation. Okay. So we could start with. So we start with the virial expansion. Okay, so we know for virial expansion PV bar by RT is nothing but 1 plus etc. Okay, where B2P, B3P, these quantities are virial coefficients, you know. Okay, and we get ideal gas equation from virial gas equation. Okay, when B2, B3, those terms are very, very small or negligible. Okay, so we could arrive to ideal gas equation in those conditions. Okay. Now from here you can write V bar is, we take the RT other side, like this. So this is V bar. Now we already know V bar is nothing but del G bar by del P at constant temperature. Okay. So this is nothing but RT times 1 by P plus like this. Okay. So we can write dg bar like this. Okay, we can further write like this. Okay, where basically what we are doing here, we are integrating from some low pressure, say P ideal, where the gas is said to behave ideally to some arbitrary pressure P. So, basically we are integrating from PID to P, where PID is very low or very small pressure, where the gas molecules they behave ideally, okay, and P is some arbitrary pressure. So, we can do the integration, we can write so we can write G prime, sorry, G bar is G naught T, or rather G T P ideal, okay, plus R T ln P by P ideal plus R T times B to P times P plus R T by 2 times B3 P T P to the 2 and so on. Okay. So, suppose this is our equation 3. Okay. So, now from equation 1 we can write G bar T P ideal nothing but G naught T plus R T ln P ideal by P naught. Okay. So, this is our this we can write. Okay. So, where G naught T is molar Gibbs energy or Gibbs free energy of an ideal gas, okay, at a pressure of P naught equals to 1 bar. So, we can write G bar T P is G naught T plus R T So, we can say that this is our equation 4, okay, and this equation 4 exact equation. Okay. Okay. This is exact equation. Okay, so equation 4 is a general equation and is valid for all gases, right? Although equation 4 is an exact equation, it varies or it differs for each gas depending on the values of B2PT, B3PT, etc. Okay. So, although equation 4 is an exact equation, but it depends or it differs for each gas. Okay. So, because this in the this for different gas molecules, the value of B2P, B3P, etc. are different. Okay. Now, from equation 4 we can write G bar Tp is nothing but G naught T plus RT ln F Pt by F naught. This is equation 5. So, what is F Pt and F naught? So, where F Pt by F naught is nothing but P by P naught, then e to the like this. Okay. And this is equation 6. Okay. And FPT is nothing but Fugacity. And in this term, non-ideality is buried. Okay. In this term, non-ideality is buried. Okay. And FPT goes to P as P goes to 0. Okay. When pressure is very, very small, then FPT goes to P. So, we need to know few things here. Okay. Note here, this is important to note. The standard state in equation 1 and in equation 4 is taken to be the same quantity. Okay. Thus, the standard state of the real gas in equation 4 is taken to be the corresponding ideal gas of ideal gas at the or at 1 bar, at 1 bar pressure. In other words, the standard state of the real gas is 1 bar after it has been adjusted to ideal behavior. So, you should note this one. Okay. The standard state in equation 1 and in equation 4 is taken to be the same quantity, they are the same quantity. Thus, the standard state of the real gas in equation 4 is taken to be the corresponding ideal gas at 1 bar pressure. Okay. In other words, the standard state of the real gas is 1 bar after it has been adjusted to ideal behavior. So, you should remember that. Okay. Thus, you can write and FPT goes to P as P goes to 0 as all gases behave ideally when P goes to 0. Okay. Very low pressure, all gases they behave ideally. Okay. Thus, the choice of standard state not only allows all gases to be brought to a single common state, but also leads to a procedure to calculate fugacity, to calculate if PT at any pressure and temperature. Okay. Thus, the choice of standard state not only allows all gases to be brought to a single common state, but also leads to a procedure to calculate F PT or fugacity at any pressure and temperature. Okay, thank you.